Yes, it's taking a little bit. Okay, it's complete. Well, thank you, everyone. Well, we are going to present Richard Kienhoefer. I don't know how to spell correctly.
It's fine. It's fine.
Yes, he is graduated from the University of Barcelona, Quantum Science and Technology Master Program, and also is undergraduate degree in physics from the University of Nevada, Reno, and currently admit at Piquet. Tell us a little bit about you, and well, you can continue with your presentation.
Yeah, thanks for introducing me. Yeah, mainly what he said. I'm in Barcelona now, and I finished the master's degree here. And um, as an admin peak, we thought it would be a good idea to kind of try to show more about, or give a presentation more about how quantum mechanics is really ingrained in quantum computing, if that's not obvious enough. And so we decided to, or I made a presentation about how the quantum mechanics axioms, or like the kind of the fundament or the ideas behind quantum mechanics, how they kind of come into quantum computing by going down each axiom and trying to show exactly where you might be able to see that in quantum computing. It might be a little short though, because so maybe like 30 minutes or so, because the axioms are fairly quick to go through, and they're fairly easy to represent in like the basic quantum computing, or in Qiskit as well. So the first few postulates, or the Dirac and von Neumann postulated the first few quantum mechanics axioms, and since then they've been modified and added to. And so the just kind of like the keywords, or like the main idea for each of the six. So the first one is about the physical system, the physical states, and mainly introducing the bracket notation. The second one is about observables. The third one's about measurements. The next one's about probability, and then the normalization, or the wave collapse. And the last one is about the time evolution of a system. So the first one is how a physical system. So at each instant of a state, the physical system can be represented by a ket, and so these kets are usually in the space of each individual of the state. And so in quantum computing, and we can see this by looking at the state of one qubit, which is the psi with a _1. The states that are represented in that are the 1 and 0 state, or the vector with 1 and 0, and the other state is the 0 and 1. As we expand the amount of qubits, we expand these amount of states, usually to the order of 2 to the n, with n being the number of qubits. And the psi2 on the bottom shows how that how that state expands out. And this relationship also gives rise to the notion of superposition. So if I switch my screen sharing to my browser here for a second. Can everybody see that? So we have an example of a 2-qubit system here. So just a very basic Bell state system. And we want to look at what the state vector of that is, and how it looks. So each time you measure it, you get one of the 4 possible states. And because we're in a Bell state, we will only get the 2. So we can see how the state of our system is represented by the state vector. So in this run, or in this measurement, we have the 0, 0 state, 0, 1, 1, 0, and 1, 1 state. And sometimes when we run it, we'll have the 1 in the other state. And so the combination of all this gives rise to the state, the ket of the entire system. And so just moving to the 3-qubit example, I just added another qubit here, and we can see that the system is much larger. So from 2 to the n, so 4 states to 8 states with 3 qubits. And we'll have the one on this point, that place, or at the end here, just what the qubit looks like. Okay. Moving back to the presentation, which is where again. We can move on to the next axiom. And so this one is about the observables. About each observable attribute of a system is described as an operator that acts on these kets, or on these states that we've shown before. And so typically in quantum mechanics, these observables are the these operators are the momentum operator, or the position operator, and even the time operator. But they're a little bit different when we look at the operators for quantum computing. These are the operators that we use are just the gates that we apply to the states. And so we have the X, Y, Z, and this image from the Qiskit website shows all the individual gates that we can apply to these kets, or to our states. And so I don't think I need to show that much for the coding part. If you just apply the gates, you're applying an operator to our state, and that will be the observable attributes of that system. The next one, the next postulate is about the measurements. So like, what do we measure when we measure a quantum system? And the only measurements that we can get are the eigenvalues and the eigenstates and the corresponding eigenstates of those observables. So the eigenvalues that we can get from our system are derived from the operations that we apply to our gate. So an example we have here is the X gate. So we have the matrix representation for that. And the only eigenstates that we can get from applying an X gate are the plus and minus state here. To get these eigenvalues, we can just take an arbitrary matrix, like a 2x2. All we need to do is subtract a value lambda from the diagonals and multiply them across. So the lambdas multiply together, and then we subtract that by the off diagonals. And by doing that, we can get a lambda, or our eigenvalues, of plus minus 1. If we take those and we multiply them by a vector, and then we equate that with the random matrix that we made, and multiply that by the same vector, we can then do some basic matrix multiplication and get the eigenvalues, or get values for x1 and x2, which then when we plug that back in, those are our eigenstates. And typically, when we're looking at the simple gates, so X gate and Y gate, and even the C0 gate, we see that that the corresponding eigenstates, or the values that we can get from those, are in the basis of these plus and minus. So that's the 0 plus 1 divided by the root 2 when we normalize it, and the 0 minus 1 state. So the ket with the 0 and 1 in them. And so we can also see on this the C0 example, when we calculate out the lambda, the eigenvalues, we get plus and minus 1. And when we then use that to calculate the eigenvectors, we get these two. So these two eigenvectors here. which then still corresponded to the plus and minus states that we see on the normal X game. And then if I stop sharing again and go back to the Jupyter notebook, kind of to show this, I'll just use the same circuit that I had before with the same state vectors, and we can get these. We can get the amount of shots, or like the results, the counts that we get from running the circuit. And so we can just get counts, and we can get the results. So we can see that it's that our states are normalized to the 1/√2. And I think I wanted to say something else about that. Yeah, so these are the only states that we can get from our by looking at the eigenvalues of the operators we have in H and the C0 gate here. Moving on to the next postulate. The fourth one is about the probability of these measurements. So the probability of obtaining an eigenstate, or one of the eigenvalues, let's just call it AN, from these observables is given by the square of the inverse. So the value right here, and the product of our ket. So if we take the eigenstates that we get and take the inner product with the state in total and just absolute squared it, we get the probability that we're able to get that specific state. So each of these ANs are the state is the value of the 1 or the -1, and the corresponding eigenvalues that we get from there. Another thing to note about this is that if you inner product the same thing together, you'll always get 1 if they're unitary, and if you take the inner product of one eigenvalue or one state with an orthogonal an equivalent other state, you'll get a delta function of these two corresponding states. Another thing to note about the probability is that the expansion expansion of states that I was showing before, where you can have the 1, 0 with some value plus the 0, 1 state with another value, can be expanded to all the other possible combinations of qubits. And that value that we have in front is the probability amplitude. And these probability amplitudes for each of those, each state within your state of states, or the state of states, with the space of your states, the combination of those always has to be equal to 1 or 100%. So if you have to have the absolute squared of it. So you have to take the probability of that plus the probability of the other one squared, adding them together has to always be 1. And so that's usually where we also can calculate the normalization values of each of those states. And because the other examples that I showed with the Jupyter notebook are fairly equivalent, or you can kind of see the percentage or the probabilities of them with the counts. I wanted to kind of show more attention to how we're able to use that with the Shor's algorithm, the measurement process of the Shor's algorithm, just with this simple picture. This is from Jay Hittery's quantum computing and applied approach, his textbook. And so when we have an array of probabilities, whether positive or negative, once we apply the Shor's algorithm, we're able to move those probabilities around in order to get the result that we need. And so from this random kind of periodic percentages, all those other ones get suppressed, and we really pump up the probability that we want to figure out or that we want to find. And that's one way that we're able to use probability to do applied measurements. And always as well, with the summating everything to be equal to 100%. All these smaller all the other values that we don't want have like a very small probability, while the main one that we want is only at 0.99. And so the addition of all these probabilities together should be equal to 1 or 100%. So everything's accounted for. The next one is the wave collapse postulate of quantum mechanics. So immediately after measuring a certain observable, once you receive that value, the state of the system, usually it normalizes to the corresponding eigenstate. So when you measure something, it will usually the wave function collapses into that singular value. And so if your state is a continuous wave function, and you measure it, if you measure it, you get one value, it collapses to that specific discrete value. And that's also where the quantum comes from for there. And this isn't exactly 100% from a mathematical basis. This is a lot of it comes from observables as well. And so the last postulate for this is the time evolution postulate. So as time evolves, or the time evolution of a quantum system preserves the normalization of the associated ket or the associated state. And so when you go from one time to another, typically the normalization, the numbers that we have, or the probabilities usually, not the probabilities, but the normalization constants usually maintain themselves. And so two ways that we can see this is in the math side is through Schrodinger's equation, where you have the derivative of one of the kets at a certain time. And another one is how you actually calculate the time evolution. So by taking this time evolution operator, we can go from a time 0 to a time t, and that's equal to our state at time t. And it's kind of hard to represent this in a quantum computing kind of way. And so the main demonstration of this and like how it's used in quantum computing is to reset the qubits. And so if you if you see this graph, you send a microwave pulse to one of the qubits, and it gets excited. And then over time, that excitement drops back down to 0 at like a ground level. And you can find this paper there, but that's the main gist of that. And yeah, and those are the 6 postulates of quantum computing and kind of how they relate to quantum mechanics. And I'm open to questions.
Sure, thank you, Richard, for your interesting presentation. And I don't know if someone have a question in English, Spanish.
There's a nice PDF text that I found that I can also link if anyone just wants to read them exactly from there instead of through a presentation. It might be easier for some people.
Mm-hmm. Wait seconds. Yes, this one. There's a question. Brian Garcia said how we can implement the off-diagonal element of the density matrix and how to use these values in quantum circuits. Really interesting question.
Chat. Let me see. How do you interpret the off-diagonal elements of the density matrix and how do you use the values? Let me think about that. God. I'm not exactly sure how you'll use those off-diagonal elements. Usually they're to move from, I guess from to move one state of the qubit to the other, or one part of the qubit, because you have the 0 and 1 state in one qubit, and if you're doing the diagonal elements correspond to the if you're looking at like the eigenvalues or the eigenvectors, you have the like x1 and x2, and that's usually corresponds to our 0 and 1 state. And if we're using the off diagonals, that's kind of like moving over the values from one side, from one of the states to the other, kind of. And so you can see that in the like the bit flip, where you have the where you only have the off diagonal elements, I think, because in some
The off-diagonal element of the density matrix represents the coherence of a state in an ideal quantum computer. Those terms will always be at the max value. Only noise will decrease their value, causing the coherence.
All right. Thanks for answering the question for me. Yeah, I think it's maybe a little bit outside the scope of what I had just presented, but it's also a very interesting question.
All right.
Right. Yeah. If there's no more questions, you can also leave them in the Discord on the Tier 20, or any other channels.
Sure. I don't know why no one question mark.
It's not that like deep of a presentation, but it's also just to really ingrain how quantum mechanics really plays a role, and like how it links up to quantum computing, like where all the individual little elements come from. So I hope everyone got something out of that.
Yeah, thank you very much, Richie. Well, also we are continuing with the following presentation. If you have a late question, you can also use Discord to send us the question. And our presenter can help you with any question. Thank you very much,
All right.
and see you there.
All right. Bye.
Mm.